Okay, afternoon everyone. This week's tutorial will be looking at your assignment, going over the concepts, going over the different types of analysis that we'll be doing. So if you have any questions about any of the specific analysis that we have to do, if you want me to cover one of them in detail, I can. So just let me know now so that I can focus my energies there. Because there's a lot of things to cover. So I mean, I can't cover all of them. So if there's a particular one that you have a problem with, just let me know so I can focus on that. Okay, so this assignment we are required to size a Planche coupling. By size, I mean we have to find out the dimensions of it so that it will be able to function properly without failing. But before we can do that, we have to first be able to identify the different types of forces that our coupling will experience during its working lifetime. Now, generally, there are three types of forces that we deal with. So what are they? What types of forces do we have?
Friction force?
Friction force is one of them, but in this case, we won't be looking at friction because friction means that there are parts moving against each other. And in the case of the coupling is fixed to the shaft pretty much. So we won't be worrying too much about friction, but there are three others that we will be looking at. Torque will produce the force, or torque is a function of force, but it isn't a force on its own. Right? Torque is equal to force times distance. But the types of forces that we will face, there are three different types. Contact force again is related to friction force. So not really contact force. We have something called shear force, compressive force, and tensile force. So three main types, and those are the three types that we'll be using in this assignment. Right, so let's look at a round piece of rod, metal rod. Compressive and tensile are known as normal forces, meaning they act perpendicular to the stressed surface. So if this is the stressed surface with an area A, the force acts perpendicular to that surface, meaning it acts at 90 degrees to that surface. All right. So any force that is pulling the surface is a tensile force. Any force that is pushing, so if the force was going into the surface, that means that's a compressive force. And if the force is parallel to the shear surface, or is parallel to the stressed surface, then we're looking at a shear force. So those are the three different types of forces that we'll be looking at. All right, second question. How do we know when our design is good enough? How do we know when our design will be able to withstand the forces that it will during its lifetime? As an engineer or as a design engineer, you have to keep two things in mind. Firstly, safety. Safety is the most important thing. Whatever you design, whatever you're making, whatever machine, component, whatever it is, you always have to make sure it's safe. Safe for the public, safe for the client, safe for the consumer, whatever it is, it has to be safe. And the second thing you have to keep in mind is the cost. So you're always trying to find a balance between the two, because these two generally you can't have something that's very safe and very cheap. Usually, if you are going to try to make something safe, you have to spend a lot more money to make it. And if you want to try and save money, it usually means you are compromising the safety of the part. So all the while we're doing design, we have to try and find the balance between safety and cost effectiveness. So hopefully you've all been attending the lectures and you know a little bit about the stress strain curve. Now, for you guys who are doing mechanical or civil engineering, this is the fundamentals. This is the foundation. Understanding the stress strain curve. The stress strain curve gives the relationship between the stress and strain of a material when it experiences some kind of force. Okay. So the stress strain curve is broken into two different regions. We have the elastic region and the plastic region. Now, at this point here, there is no force being applied to our part. Let's look at this part as an example. Imagine that there is no force being applied. At this point, it is zero. As we start to increase the force, the stress starts to increase. And as the stress increases, the strain increases by the same amount. All right, these two have a directly proportional relationship in the elastic region. That means when you reach a certain point and you take away the force, the part will go back to its original shape. That's the main material property that comes about when we are in the elastic region. Stress and strain are directly proportional, and as soon as you remove the force, the part will go back to its original shape. But there is a certain point where that relationship doesn't exist anymore. That point is called the yield strength, or the yield stress of the material. And at this value, the material cannot withstand any more stress, and it will start to enter the plastic region. And in the plastic region, there is no direct relationship between stress and strain, which means if you continue to load it with some force and it goes beyond the yield strength and enters the plastic region, as soon as you release that stress, it won't come back to its original shape. It'll have changed shape slightly, depending on the amount of stress that you apply, amount of force that you apply. Now, in engineering terms, as soon as a part enters the plastic region, it is considered a failure because nobody wants to design a component that will change its original shape as it's being used. Usually when it changes shape, that means you have to change the part. So we always try and design our components to be within the elastic region and with a working stress below the yield stress. Okay. So that is how we tell if our design is adequate or not. If the working stress is less than the yield stress. Now, can anybody tell me what the factor of safety is? What is the factor of safety? The factor of safety is the direct relationship between the yield stress and the working stress. Okay, it's the ratio of yield stress to working stress. Let's say, for example, we have a factor of safety of 1. That would mean our yield stress is equal to our working stress. Now you tell me, does that sound like a good idea to have your working stress, so the stress that your part will experience through its lifetime, equal to the yield stress of the material? That does seem like a good idea to you? To have the yield stress equal to the working stress? Yes, Joash, you've got the right idea. If we have our working stress equal to our yield stress, that means we don't have any room for error. That means if there is some kind of a case where there might be just a little bit extra load, there might be an impact load, or maybe the shaft is rotating a little bit faster than we thought. That means the forces involved will be increased, and our working stress will be greater than our yield stress, meaning that our part will fail, and yes, we'll have to replace it. It won't last long. So the factor of safety is basically just some kind of way of giving us a little bit of breathing room, a little bit of room for error. Now, depending on the application, you can have factors of safety of 1.2, 1.5, 2, 10, 100, you know, so long as it's greater than 1, it's a factor of safety. However, your next question might be, why don't we just design everything to have a factor of safety of 10, and we don't worry about changing the factor of safety for different occasions? The reason for that is coming back to the balance between safety and cost. If we give everything a factor of safety of 10, it'll mean that everything will cost a lot more than it needs to. So that's why we look at a case-by-case basis. Depending on the application, depending on the material, will influence the factor of safety that we have to use. So if we know the materials very well and we know the types of forces that it will experience during its working lifetime, then we put a lower factor of safety. But for something where a lot of people's lives are at risk, where there might be some unknown forces, something that we can't predict, we would put a higher factor of safety. So like for a bridge, you might have a factor of safety of, say, 3 or 4. For a plane, maybe 10. And for a coupling, maybe a factor of safety of 1.2 is good enough. So that's the reason for having a factor of safety. It's basically like drawing a limit. How safe do we have to make it? Okay? So our assignment is broken down into 5 different types of analysis. We have the torque analysis, key analysis, hub analysis, web analysis, and the bolt analysis. And the order of those things has to go in that order. We have to start with the torque analysis because that torque will help us find our force for each one of the different analysis that we do. Then we have to do the key, the hub, the web, and the bolt in that order. The reason for that is because that is the order of the load path. So the load is originating from the center of the shaft, and it goes from the shaft to the key, from the key to the hub, from the hub to the web, from the web to the bolt, and then out the other side to the center of the second shaft that we're trying to move. All right. If we weren't given the shaft dimensions by the client, we would also do a shaft analysis, but we didn't have to do that for this assignment. Luckily, you just have to start from key analysis, hub, web, bolt. So is any one of these ones here that you're having problems with? so I can focus on that analysis. The key and hub analysis. Okay, so I'll focus on the key and hub in this tutorial session. Okay, so firstly, the key analysis. So once you've done your torque analysis, you come up with your torque, you can move into your key analysis. First step in the key analysis is you have to find the force that will be acting on the key. All right. So we all know the relationship between torque and force is torque is equal to force times distance. Right? What type of force will we be expecting here? The shaft will be rotating this direction. What type of force will we be looking at? The force will be acting in this direction. So in this case, we are talking about a shear force. Shear force. And the distance is from the center of the shaft to the center of the key. And we are assuming that half of the key is down here in the slot in the shaft, and half of the key is above. So the distance from the center of the shaft to the center of the key is just the radius of the shaft. So the shaft radius we're given, in the shaft diameter we've been given, is 48 millimeters. So this is the diameter. So therefore the radius is 24 millimeters. Using that, we can now calculate our force. All right. Once we have our force, we can now apply the stress equation to calculate for the length of the key, which is what we're trying to find at the end of the key analysis. Now remember, we're looking at shear force, so we'll be looking at the shear stress of the material. So shear stress is equal to the shear force divided by the area. The area being this red section here. This area has the dimensions of this and this. This is the width of the key, and this is the length of the key. All right, so area is equal to the width of key multiplied by the length of key. We know our shear force, shear stress we can get from the information given to us. So we know that the key is made out of mild steel, and we're looking at the shear strength. So we'll look at the shear strength of mild steel, which is 28 megapascals. We'll substitute that in place of this shear stress value. So we'll have 28 mega, so 28 times 10 to the power of 6 equal to shear force, whatever your shear force is from there, divided by your width of key times length of key. Now your width of key, you can find also from the data sheet given to you. It says standard key section dimensions and tolerances. For a shaft size of anywhere between 44 and 50, we have a width of 14 millimeters and a thickness of 9 millimeters. So our key width in this case is 14 millimeters, and our length of key is the one that we're trying to find. So if we rewrite it, its length of key is equal to shear force divided by multiplied by 14 millimeters. Okay, and that's how you do the key analysis. Now, if you come here and you find that your key length is 50.8 millimeters, you would have to round this up, because if you gave this dimension to a manufacturer, they might swear at you, because 50.8 is very, very precise, and not a lot of manufacturers can come to those kind of very precise dimensions. So you would probably have to round it up. And even if you round it up to 51, that is still a bit too precise. Most manufacturers like to work in multiples of 5. So you're either going to go like 5, 10, 15, 20, 25, 30, so on and so forth. So you'd probably round this up to about 55 millimeters. You could even go up to 60, but bear in mind the factor of safety, okay? The longer you make your length of key, it will mean the longer you have to make your hub. And, you know, the bigger you make your hub, the more expensive it'll be. So 55 is about right. Okay, so that's the key analysis. Now I'll move on to the hub analysis. Are there any questions from the key analysis?
Sir,
Yes.
If we use if instead of the 28 to exponent positive 6, can't we use the torque we calculated from the torque analysis and just find the area? Because we'll be finding the shear force of the key analysis in part 1. So can't we just directly find the area by substituting torque and shear force?
Can we substitute torque and shear force instead of shear stress? So this value here is not T. Okay, this is not T. This is tau. This is a tau on its own. Tau is so for shear, it's called tau, and for tensile compressive, it's called sigma. So it's not T, it's actually tau. So we can't actually substitute T in place of this shear stress value.
Okay.
So, all right, moving on to the hub analysis, if there are no more questions. So the hub analysis is a bit of a longer one. You have to make some assumptions along the way when you calculate for your hub thickness. The hub thickness is what we're trying to find here. By hub thickness, I mean this thickness from here to here. This is the hub thickness. The thickness of the hub above the key. So first we will try and calculate for our force. So our force is acting in this direction, with our shaft rotating this way. So this is acting normal to the red surface, which is our stressed surface. So this is a tensile force. And torque is equal to force times distance. Torque is equal to force times distance. So force will be equal to torque divided by distance. And this distance is taken from the center of the shaft to the center of that area. So you'll be going your shaft radius plus half of your key, because half of your key is protruding above the shaft. So key height divided by 2, plus your hub thickness divided by 2. All right. Now, this hub thickness is something that you have to assume. You assume this value. You say, okay, I think the hub thickness should be, let's say, 16 millimeters. I think it should be 16 millimeters. So you make that assumption and you plug it into this formula, and then you solve for your force. Once you have your tensile force, you plug it into the stress equation. So for tensile stress, it is stress is equal to force over area, which will be equal to Ft divided by the area is the hub thickness, multiplied by the length of the key, because the hub covers the whole key. Our shear stress value, or not our shear stress, our normal stress value, or our tensile stress value, we can take from the data given to us. So the information says that cast iron has a tensile strength of 8 megapascals. Remember, the hub is made out of cast iron. Only the key is made out of mild steel. So 8 megapascals. So you put that in place of our tensile stress. And we try and solve for HT again. So we make HT the subject of the formula. And this is actual HT, or recommended HT. Okay. And once you have this recommended height of your hub, or thickness of your hub, you then have to do the calculation again for a different assumed thickness. And you go on back and forth until you reach an appropriate recommended thickness. Now I'll show you an Excel sheet which does this calculation for us. So using Excel is a very powerful tool, and it's probably the one that you're going to use most as an engineer, because you can do a lot of complex calculations very quickly by just changing a few values. Right, so this calculation sheet takes into account the torque that we're applying. We enter whatever thickness we want. So in our case, 0.016, 16 millimeters. It'll calculate the force for us. We enter the tensile strength, and it'll calculate the recommended hub height. The only thing that this sheet does extra is it calculates the factor of safety. Factor of safety based on your assumed thickness. All right, so let's go press enter, and we see that we have this force that will be acting. Using the same calculation that we just did, it'll calculate the force for us, and it'll give us an assumed thickness, or recommended thickness, of 29.7 millimeters. So it's saying 16 isn't enough. You need to use 29 millimeters if you're going to have this kind of force. But your factor of safety will be 0.5 if you use this thickness, 16 millimeters. 0.5 is less than 1, and that's not what we want. So let's increase the thickness again and do the same calculation. Let's change the thickness now to 0.026, 26 millimeters. Now at this point, you can see that the hub thickness, so the recommended thickness, is closer to our assumed thickness, and the factor of safety is almost 1. So this tells us that when the hub thickness above the key is 26 millimeters, the factor of safety will be 1. So our design should have a thickness greater than 26 millimeters. So now let's go back to our assignment question. And let's look at different types of factors of safety which we might want to apply. So we need a factor of safety greater than 1, but we don't know which factor of safety we're going to use. That's where this table comes in handy. The first one, factor of safety of 1.25 to 1.5, is for reliable materials under controllable conditions, which is what we're dealing with here in this assignment. We know the material and we know the conditions. So we want a factor of safety of 1.25 to 1.5. Now going back to our Excel sheet, let's enter a thickness of 0.031 or 31 millimeters. We press enter, we can see that the factor of safety is now 1.257, which is within the region which we were hoping for. So we can say that 31 millimeters is the best hub thickness to use. Of course, we could use an even thicker hub thickness because it says from 1.25 to 1.5. So let's say a hub thickness of 0.035. And we get a factor of safety of 1.48, which is just below the end of the limit, which is 1.5. 1.25 to 1.5 is the factor of safety limit, and this one gives a factor of safety of 1.48, which means that if we are going to design this part, our maximum hub thickness can be 35 and our minimum should be 31. All right. The calculation for the factor of safety is just your yield stress divided by the force, which is then divided by the assumed thickness times your key length. All right. You could do all those calculations by hand. That's fine. I just wanted to show you quickly why we have to keep doing different calculations, why we can't just stick with the first calculation that we do. So once we have our hub thickness in this case is 31 millimeters. We now have to define our hub diameter. And our hub diameter is from the center of the shaft. So hub diameter will be equal to hub radius times 2, which will be equal to shaft radius plus key height divided by 2 plus hub thickness. Not hub thickness divided by 2, hub thickness. Whole thing multiplied by 2. So when you finish your hub analysis, this is what you should be coming out with, a value for your hub diameter. Okay, guys? So the session's about to end. Please just leave your name and ID numbers in the chat, along with, if you're not part of this tutorial session, just also include what tutorial session you belong to so that I can track your attendance. I hope this has been beneficial. The recording will be uploaded to YouTube, and I'll send you guys the link so you can have a look back and see. Next week, I think we'll also be covering the assignments. So if you still have questions next week, we can cover that then next week. Are there any questions before we end? We've got 1 minute.
Thank you, sir.
Okay, thank you guys. Have a blessed weekend, and I'll see you all next week.
Sir, have a blessed weekend. Thank you.